Welcome to AP Precalculus, where today we're diving into a fundamental concept: how linear and exponential functions model change. We'll be exploring the change in linear and exponential functions. By the end of this lesson, you will be able to construct comparable functions to model arithmetic and geometric sequences. Our first objective is to construct these comparable functions. You will also be able to compare and contrast linear and exponential functions based on their rates of change and how they are determined. And our second objective is to compare these two types of functions. Let's start with linear functions. These are used to model arithmetic sequences. Linear functions model arithmetic sequences. Remember the standard slope-intercept form of a linear function? It's f of x equals mx plus b. This form tells us two things. B is the y-intercept, which is the initial value at x equals 0, and m is the slope, representing a constant rate of change. So, b is the initial value, and m is the constant rate of change. Now, let's look at an arithmetic sequence. Its formula for the nth term is very similar. It's a sub n equals a sub 0 plus dn. Here, a sub 0 is the initial term, and d is the common difference, the constant value added to get the next term. Do you see the resemblance? A sub 0 is the initial value, and d is the common difference. In essence, the slope in a linear function is analogous to the common difference d in an arithmetic sequence. They both describe the constant amount added or subtracted at each step. So, let's connect these ideas. Imagine we have a sequence, and we want to find its corresponding linear function. Let's work through an example. Consider the arithmetic sequence: 5, 8, 11, 14, and so on. Our sequence is 5, 8, 11, 14. The first step is to check if it's truly arithmetic by finding the first differences. Let's find the first differences. 8 minus 5 is 3. 11 8 is 3. 14 minus 11 is 3. The difference is constant. Because the first differences are constant, we know the relationship is linear. This constant difference, 3, is our slope mm. So our slope m is 3. Next, we need the initial value b. This is the value of the function when x is 0. Our sequence starts at x equals 1. We need the y-intercept, which is the value at x equals 0. Our sequence starts at n equals 1, with the value 5. Since the common difference is 3, to find the value at n equals 0, we subtract 3 from the first term. 5 minus 3 is 2, so our initial value b is 2. b equals the first term minus the common difference, which is 5 minus 3, or 2. Now we have our slope m and our y-intercept b. We can construct our linear function f of x equals 3x plus 2. This function perfectly models our arithmetic sequence. Now let's switch gears to exponential functions. These are used to model geometric sequences. Exponential functions model geometric sequences. The standard form of an exponential function is f of x equals a times b to the power of x. In this form, a is the initial value when x is 0, and b is the constant ratio by which the value of the function is multiplied for each unit increase in x. This is often called the growth or decay factor. So, a is the initial value, and b is the constant ratio. Let's compare this to a geometric sequence. Its formula is g sub n equals g sub 0 times r to the power of n. Here, g sub 0 is the initial term, and r is the common ratio, the constant value by which we multiply to get the next term. Again, the parallel is clear. G sub 0 is the initial term, and r is the common ratio. The constant ratio b in the exponential function is analogous to the common ratio r in the geometric sequence. Both define the constant multiplicative factor at each step. Let's see this in action by turning a geometric sequence into an exponential function. We'll follow a similar process to our last example. Consider the geometric sequence: 4, 12, 36, 108, and so on. Our sequence is 4, 12, 36, 108. To verify it's geometric, we check the ratios between consecutive terms. Let's find the ratios. 12 divided by 4 is 3. 36 divided by 12 is 3. 108 divided by 36 is 3. The ratio is constant. Since the ratio is constant, we know the relationship is exponential. This constant ratio, 3, is our base b. So, our base b is 3. Next, we need the initial value a, the value of the function when x is 0. Our sequence starts at n equals 1 with the value 4. To find the value at n equals 0, we perform the reverse operation. Since we multiply by 3 to go forward, we divide by 3 to go backward. 4 divided by 3 is 4/3. So, our initial value a is 4/3. A equals the first term divided by the common ratio, which is 4 divided by 3, or 4/3. With our base b and initial value a, we can write the exponential function. The function is f of x equals 4/3 times 3 to the power of x. This exponential function faithfully models the geometric sequence. So, we've seen the connection. Now let's look at a critical distinction. Domains. This is where functions and sequences differ. We need to understand the difference between discrete and continuous domains. A sequence, like 5, 8, 11, has a discrete domain. The variable n can only take integer values. 1, 2, 3, and so on. You can have a first term, but not a 1.5th term. The domain is the set of positive integers. The domain for a sequence is discrete, consisting only of integers. A function, like f of x equals 3x plus 2, on the other hand has a continuous domain. The variable x can be any real number. 1, 1.5, pi, -17. The domain is the set of all real numbers. The domain for a function is continuous, consisting of all real numbers. Visually, the graph of an arithmetic or geometric sequence is a series of isolated dots. The graph of its corresponding linear or exponential function is a smooth, continuous line or curve connecting those dots. This distinction is crucial when modeling real-world situations. If your quantity changes only in whole number increments, like the number of people, you use a sequence. If it changes smoothly over time, like temperature or money in an account, you use a function. Now, let's achieve our second learning objective, comparing these functions. We'll now compare linear and exponential functions. The core difference lies in their rate of change. Linear functions have a constant rate of change. This means that for every unit increase in x, the value of the function changes by the same constant amount. Exponential functions, however, have a constant proportional change. The amount of change is not constant, but the factor by which the function changes is constant. This means that for every unit increase in x, the value of the function is multiplied by the same constant ratio. Think of it this way. Linear is based on addition, while exponential is based on multiplication. This leads to the fundamental shape of their graphs. Here we see their characteristic graphs. Linear growth appears as a straight line, rising steadily. Exponential growth, in contrast, appears as a curve that starts slow and then becomes incredibly steep. That's the power of multiplication. So, how can you tell which type of function or sequence you have? The key is to analyze the data. There are two simple tests you can always use. First, check the first differences. If the differences between consecutive y values are constant, it's linear. Check the first differences. If they are constant, you have a linear relationship. Second, check the ratios. If the ratios of consecutive y values are constant, it's exponential. Check the ratios. If they are constant, you have an exponential relationship. It's important to remember that you can define a unique linear or exponential function if you have just two distinct points or values. That's all you need to find the initial value and the rate or ratio of change. Finally, whenever you're modeling a problem, always interpret your initial value and rate or ratio of change in the context of the units given. Understanding the units helps ensure your model makes sense in the real world. Let's quickly recap what we've learned today. We started by seeing that linear functions, like f of x equals mx plus b, are the continuous version of arithmetic sequences. The slope-intercept form f of x equals mx plus b resembles the arithmetic sequence formula a sub n equals a sub 0 plus dn. And we learned that exponential functions, f of x equals ab to the x, are the continuous version of geometric sequences. The exponential form f of x equals ab to the x parallels the geometric sequence formula g sub n equals g sub 0 r to the n. We also highlighted the key difference in their domains. Sequences are discrete, while functions are continuous. Sequences have a discrete domain consisting only of integers, while functions have a continuous domain of all real numbers. And most importantly, we compared them. Linear functions change by adding a constant amount, giving them a constant rate of change, and a straight line graph. Linear functions are based on addition, have a constant rate of change, and a straight line graph. Exponential functions change by multiplying by a constant amount, giving them a constant proportional change, and a curved graph that grows very rapidly. Exponential functions are based on multiplication, have a constant proportional change, and a curved graph. Understanding these fundamental similarities and differences is essential for modeling and solving real-world problems in AP Precalculus. Great job today! Just a moment, there's one more important form that's very useful in AP Precalculus: the point-slope and point-ratio forms. For linear functions, you might already know the point-slope form. It's u minus y sub 1 equals m times the quantity x minus x sub 1. This form is used when you know the slope m and any single point x sub 1, y sub 1 on the line. Now, let's derive a similar form for exponential functions. We'll call this the point-ratio form. Start with our standard form, f of x equals ab to the x. Let's say we know one point on the graph, x sub 1, f of x sub 1. From our standard form, f of x1 equals ab to the x1. We can solve this for a by dividing by b to the x1. So, a equals f of x1 divided by b to the x1. This gives us a equals f of x1 over b to the x1. Now, substitute this expression for a back into the original function. We get f of x equals the fraction f of x1 over b to the x1, all multiplied by b to the x. Using the rules of exponents, we can simplify this. This simplifies to f of x equals f of x1 times b to the power of x minus x sub 1. This is our point-ratio form for an exponential function. Similar to the point-slope form, the point-ratio form is incredibly useful when you know the constant ratio b and any single point, x sub 1 f of x sub 1, on the graph. It allows you to build the exponential function directly without first finding the y-intercept a. This is a powerful tool to add to your toolkit for solving problems in AP Precalculus.